Let's talk about nonlinear control systems. Phase plane analysis, phase portraits. The phase plane method is concerned with the graphical study of second order autonomous systems of this type. They're autonomous because time explicitly does not enter the argument for f1 or f2 functions. x1 and x2 are called the states of the system. The functions f1 and f2 are normally nonlinear functions of the states. If they are linear, then it becomes a linear system. Geometrically, the state space of the system is a plane having x1 and x2 as coordinates, and this plane is called the phase plane. Normally, linear combinations of x1 and x2 are called states. This is a simple spring mass system. This is mass m, this is the spring. The governing differential equation is obtained by applying Newton's laws of motion to the system, the spring mass system, and this is that governing differential equation. So when states are defined using the variable x is the displacement of the mass from the equilibrium point of oscillation of the system, and the states are defined in the following fashion. x1 dot is defined as x2, and x2 dot, which is x1 double dot, will work out to be minus omega squared x1 from the governing equation. So this is the state space representation or phase space representation of the spring mass system. And this is the phase portrait. We'll look at this in a few slides later. Singular points are important concepts on the phase plane. A singular point is an equilibrium point in the phase plane. A singular point is defined as the point where the system can stay forever, which implies that x dot must be 0, where x is a vector here, so which means that all of the states x1 dot, x2 dot, x3 dot, x2 dot will be 0 at the singular point. So it follows from the set of equations we wrote previously, these equations, that f1 of x1 and x2 must be 0 and f2 of x1 and x2 must be 0 too. So we need to solve these two simultaneously to get the equilibrium points of the system. The equilibrium points are singular points because at the equilibrium points, the slope given by dx2 by dx1, so if you look at these equations, slope becomes dx2 by dx1, which is f2 by f1. At this singular point, equilibrium points, the slope becomes 0 by 0, indeterminate. So which is why an equilibrium point is a singular point. Let's look at a nonlinear second order system of this type. It's a nonlinear system because x squared is entering the equation. If x squared didn't exist, it would have been a linear system. So this is the phase portrait of the system by defining the state variables. X and x dot are the state variables. So this is the region shown through the hash. This region is a convergence region. The equilibrium points of the system are singular points, which are 0, 0 and minus 3, 0. It may be seen that the first singular point is actually stable because all the trajectories are converging to 0, whereas the minus 3, 0 point is unstable because there are trajectories which are going away, diverging from minus 3, 0. It's an unstable point. Single order systems, that is x dot plus fx equal to 0, which is a first order system in single variable, may also be represented on the phase plane. The phase plane is a plane because it is defined by using second order differential equation, which is leading to two state variables, and hence it is represented on a plane with x1 and x2 as states. A first order system has a single variable. So it turns out that such systems may only be represented as a single trajectory, only one trajectory for a first order system on the phase plane. So if you look at this example, x dot equal to minus 4x plus x cubed, the singular points will be obtained by equating the right hand side to 0, and the singular points occur at x equal to 0 and x equal to plus or minus 2. So it may be shown that the origin is stable, whereas the other two zero crossings are unstable singular equilibrium points. Symmetry elements of the function allow simplification of the phase portrait drawing procedures. So if I look at this system, the symmetry elements of this function will simplify the phase portrait drawing procedures. So let's look at some symmetries of this. So symmetry about x1 axis occurs when the function f satisfies this condition. A symmetry about x2 axis occurs when the function satisfies this symmetry condition. This is symmetry about the origin. So reversing the signs of x1 and x2 and reversing the sign of the function returns the same value of the function, is the condition for symmetry about the origin. So the spring mass system has both of these symmetries, the first symmetry and the second symmetry also, about x1 and x2 axis. Phase portrait construction procedure. So the previously discussed symmetry elements will simplify the construction procedure for the phase portrait. So analytically, phase portrait may be drawn by integrating the two equations whenever they are integrable, whenever a method for integration is known. So that normally leads to a function of this type. So the equations may be solved also, and the equations in turn will lead to a function of this type, which may be drawn, leading to the phase portrait of the system. The other procedure is a graphical procedure. The other procedure is forming this differential equation. This may be also integrable sometimes through variable separable technique or some other technique. If not integrable, then a graphical procedure for visualizing this exists. And that procedure is called isoclines method. We'll look at that shortly. So a simple example for the phase portrait construction is the spring mass system, whose governing differential equation was shown in the previous slide. And by defining in this fashion, by rewriting x double dot in this fashion, it's possible to write the equation as this, which can be integrated, leading to the circles, so which was shown in the previous slide. Let's look at a satellite control system. The satellite is here. So this is the antenna which is supposed to view along the positive y-axis that way. So whenever the satellite deviates from the intended viewing area, these rockets fire, bringing the satellite antenna back to the required direction. So now an error has occurred because the satellite has turned a small angle to the right side. Then the rockets fire, these two rockets fire, to bring back the antenna to the intended viewing direction. So this can be modeled by using the Newton-Euler equation, torque equal to I alpha. The torque equals I times angular acceleration. This equation is used. So for simplicity, we assume that the moment of inertia is unit, so that the governing equation becomes, and that the torque applied is a constant. When the angle is positive, a positive u, or the torque, is applied, a constant. When the angle is negative, a negative u is applied to bring it back to the intended viewing direction. Okay, so the control is nonlinear. So when theta is positive, u is positive. When theta is negative, u is negative. So that u integrates twice to get back theta. So the governing equation is this, theta double dot equal to u, coming from this equation, torque equal to I alpha. So you integrate this twice to get the value of theta. So that's what is happening in this block. This is the control action, depending on the error value. So it may be seen that because the right-hand side is a constant, this is integrable 2 times to give theta as a function of time. It's a parabola. So because the control being positive or positive constant or negative constant is the control action, it turns out for the 2 cases, the phase trajectories are series of parabolas, which occur like this. For negative u and positive u, these are the 2 types of parabolas. So if I put everything together, I have the parabolic trajectories as the phase portrait of this satellite control system, the very simple satellite control system. The method of isoclines is a graphical method for constructing the phase portraits. So I have this equation. It may happen that this equation is not integrable or the method of integration is not known, in which case the isocline method is very useful. Set dx2 by dx1 equal to alpha, so that I have this equation now, f2 minus alpha x1, alpha f1 equal to 0. Because alpha is a constant and f1 and f2 are known functions, this can be drawn. And along that trajectory, we draw tiny segments of slope equal to alpha. I'll demonstrate this in an example shortly. So small segments of a constant angle alpha are drawn along the entire trajectory defined by f2 minus alpha f1 equal to 0. So a simple example will clarify that. So if I look at the spring mass system, which has this equation describing it, so I can put the two together, x2 dx2. Here, okay, now you take this equal to alpha, so that the equation of the isocline becomes this one, x1 plus alpha x2 equal to 0. So in the isocline method, we put dx2 by dx1 as alpha and couple the functions f1 and f2 as shown here. So that's what is happening here. That equation works out to be this. So that for each value of alpha, I have a straight line going through the origin, and along the line, I draw segments with tiny segments which corresponds to alpha value. So for this will happen, this line occurs when alpha is minus 1. Because the equation of this line is x2 minus x1. So alpha is minus 1. So the angle is 135 degrees. 135 degrees. So here, this is slope is positive. So accordingly, set the value of alpha, draw the line, and draw tiny segments representing the value of alpha along that line. Now let's look at the well-known van der Pol oscillator, van der Pol equation. This is a second-order nonlinear ordinary differential equation. When it's written in the state space form, I have this representation. Because it's nonlinear, it's not directly integrable, so we may use the method of isoclines to see its trajectory. So put this equal to alpha, so that I have this equation, which may now be plotted by varying the value of alpha, and on each trajectory, plotting the slope value corresponding to that trajectory. So this is the phase plane representation or phase portrait of the van der Pol oscillator. So these are the isoclines. So the constant tiny segment represents the slope value corresponding to this trajectory. The isoclines may be used, so all of these isoclines can be used for drawing the trajectory itself. So if the isoclines are close enough, closely drawn, then the direction of the slope along each isocline may be used to approximately draw the trajectory. So the van der Pol oscillator is drawn here by using the knowledge of the isoclines. The slope information on each isocline is used for drawing this. So this oscillator has very interesting nonlinear dynamics. It has a limit cycle oscillation. So this dark trajectory here is a closed isolated trajectory, which is a limit cycle. So we see the various values of alpha and the corresponding isoclines here. They're marked here. It is possible to determine the time information from the phase portrait by using this equation. The time may be obtained from this. Small delta t is approximately delta x by x dot. So this, upon integrating this by passing into differentials, assuming suitable conditions, the time may be obtained by doing this integration. So the time difference between two locations, t0 and our future location t, is simply the integral of dx by x dot. So just draw the 1 over x curve, 1 over x dot curve as a function of x. The area under that curve gives the time consumed. So if we plot a phase plane portrait with new coordinates, x and 1 over x dot, then the area under the curve is the time interval. Let's look at the linear systems. A general form of a linear system is this: x1 dot is ax1 plus bx2, x2 dot is cx1 plus dx2. So elimination can be made between these two equations. Differentiation and elimination can be made to obtain everything in terms of a single variable. Obtain the single differential equation by eliminating the second variable from these two simultaneous equations. And we have an equation in terms of x1 only. Likewise, the x2 equation will be similar to this one. Let's look at the dynamics of this system. So if I look at the time history, this may be solved. The solution to this is expressed in this form: e to the lambda 1t plus e to the lambda 2t with two arbitrary constants when lambda 1 is not equal to lambda 2. It is given by this function when lambda 1 equals lambda 2. Note that the linear term t is entering the second term of this solution. When this happens when lambda 1 equals lambda 2, there is a linear solution also within the general solution. So that can be obtained by solving the characteristic equation of the linear system. So you have a linear system of this type is taken. So by taking Laplace transform, we can get the characteristic polynomial, which may be solved to get the values of lambda 1 and lambda 2, and they sit at these locations in the solution to the system equation. So these are the lambda 1 and lambda 2 values. The following four cases occur when both are real and have the same sign, positive or negative, when both are real and have opposite signs, when lambda 1 and lambda 2 are complex conjugate with non-zero real parts, when lambda 2 and lambda 1 are complex conjugates with zero real parts. So these are all the cases of the linear system. So when the lambda 1 and lambda 2 are both real but negative, strictly negative, then the solutions converge to zero, because the solution is an exponential function. This is the solution. Solutions are exponential functions. So when the lambdas are both negative, they converge to zero. When they're both positive or one of them is positive, they go to infinity, and so on. So let's look at all of them in the phase portraits. When the lambda 1 and lambda 2 are both real but both strictly positive, then it's an unstable node. The previous one is called a stable node. This is an unstable node. When both are real but they're of opposite sign, one strictly positive, one other strictly negative, then the solution is a saddle. This is the phase portrait of that system. When both are complex conjugates and have negative real part, then you have a spiraling stable focus. The solution converges to zero and it's a spiral. When the lambda 1 and lambda 2 are both complex conjugates with positive real part, then the solution, when the phase portrait, is an unstable focus with the solution spiraling outward from the origin going to infinity. When both the eigenvalues, when the lambda 1 and lambda 2 are strictly imaginary, that is, they're complex conjugates but they lie on the imaginary line with zero real part, then the solution is a center. So the phase trajectory has the concentric circles depending on the initial condition of the problem. So the phase plane analysis of linear systems says that the system has to be a stable or unstable node, a stable or unstable focus, a center, or a saddle point. So this is the entire classification of the linear system. It can't be anything more than this. New dynamics cannot occur in linear systems other than these. So if I have a nonlinear system, for instance, then I can study that system using at the point of interest. That system can be studied by shifting the origin to the point of interest and then linearizing this nonlinear system about that point of interest. So when you linearize about the point of interest, you have a linear part and some nonlinear terms appearing. So the G1 and G2 normally contain the higher order terms. So this is a Taylor series expansion for these two functions. There's a linear part and a nonlinear part with higher order terms. Limit cycles are nonlinear phenomena. They don't occur in linear systems. A limit cycle on a phase plane is defined to be a closed isolated trajectory. The word isolated is quite important. So if a limit cycle is slightly perturbed, it's no longer closed. So in that sense, it is isolated. Stable limit cycles are all trajectories in the vicinity of the limit cycle are converging to it as t tends to infinity. So this is a limit cycle here. These trajectories are converging towards the limit cycle. So the trajectory which is beginning outside is converging to the limit cycle. So also a trajectory which is starting inside is going to the limit cycle, converging to the limit cycle. So this is a limit cycle which is stable. Unstable limit cycles are all, if all trajectories in the vicinity of the limit cycle diverge from it as t goes to infinity, then the limit cycle is said to be unstable, which is happening in this case. So the inner trajectory is diverging away, the outer trajectory is also diverging away. So it's a unstable limit cycle. A semi-stable limit cycle occurs when some trajectories converge to the limit cycle and some diverge. So in this example, the inner trajectory is diverging away from the limit cycle. The outer trajectory is converging towards the limit cycle. So it's a semi-stable limit cycle. When both trajectories diverge, it's an unstable limit cycle. So let's state a theorem summarizing some of the properties of the limit cycles. If n represents the number of nodes, centers, foci enclosed by a limit cycle, and s represents the number of enclosed saddle points, then the Poincaré theorem says that if a limit cycle exists in the second order autonomous system, then n equals s plus 1. So the number of saddle points enclosed by the limit cycle plus 1 must equal the number of all other points together. That is, nodes, centers, and foci together must equal number of saddle points plus 1. If there is a limit cycle, then this must happen. There's a Poincaré-Bendixson theorem which says that if a trajectory of second order autonomous system remains in a finite region, then it has to be one of these three cases only. The trajectory goes to an equilibrium point, or the trajectory tends to an asymptotically stable limit cycle, or the trajectory itself is a limit cycle. This is the Poincaré-Bendixson theorem. So this is our system again. There's a theorem due to Bendixson which says that for a system of this type, nonlinear system of this type on the plane, no limit cycle can exist in the region whenever partial f1 with respect to x1 plus partial f2 with respect to x2 does not vanish and does not change sign. For that nonlinear system, no limit cycle can occur in the region omega if the phase plane in which the region omega of the phase plane in which this quantity